Okay, let's talk about another function, namely the rank beats function. When does one rank beat another? So I'm not going to actually type this one out because there's a longhand definition here, which is a kind of exercise in pattern matching. There are 5 different kinds of ranks, and the rank beat function has 2 arguments. So the rank beat function takes one rank, another, and tells you when one rank, the first rank, beats the second rank. When is it the first one higher than the second one? So here's how we're going to build up the definition in steps. We start by considering the case when the thing you're trying to beat is an ace. And unfortunately nothing beats an ace. So whatever card you have, you can't beat an ace. You can only at best draw with it. So rank beats anything against an ace is false. Now once we've taken care of that case, once we've taken care of the case when the second card is an ace, then we can look at the case when the first card is an ace. And the second card is then obviously not an ace, because otherwise we'd use the first equation. So if the second card is not an ace but the first one is, then we definitely beat the card. So then we get true. So then we've dealt with all of the cases involving an ace. And now we just simply go through the cases one by one, dealing with each case in turn, the king, then the queen, then the jack, and so on, all the way down to the numeric case. The numeric case is the last case. That's the case when both cards are numeric, because none of the other patterns have matched, so it can't possibly be the case that one of these is not numeric. So numeric m beats a numeric n precisely when the m value is bigger than the n. A numeric 3 beats a numeric 2, for example. And if that's not the case, well, this expression will be false, and that will be the answer to this particular function application. Okay, so it's a bit of a horror in terms of the size of the definition. And in fact, it's the kind of definition where I think 2 things would be useful. One is you'd need to really test this function to make sure you've got it right. And the second one is that you probably would like to turn on this particular non-exhaustive incomplete patterns just to check that you haven't missed any cases. Fortunately, there's a much easier way to define this function. So I'm going to define that. So this is the, and I cut and paste from over here. I don't know if I can. No, it doesn't look like it. Oh, maybe I can. There we go. Yeah. So the rank beats function, we're going to define it differently. We're going to define it by deriving an additional type class called Ord. We're going to derive the Ord functions for this. So what are the Ord functions? The type class Ord is the type class. There are lots of instances of it, but let's scroll up so we can find what's in the type class. What are the functions that characterize the gang of functions, the gang of types that have this Ord label? Well, they're the ones that have all the comparison operators together with max and min. So Ord is the ordering. So how can we derive an ordering? How could you possibly know what ordering could be reasonable? Well, you can't in general, but when you derive Ord, what you're doing is saying that the ordering that you obtain is the one according to the order in which you've listed them. So for example, jack will be less than queen, queen will be less than king. What about these guys? Well, numeric cards will be less than jack. What about 2 numeric cards? Well, 2 numeric cards will be in the less than relationship if the ints that are contained in them are also in the less than relationship. So the reason we can derive Ord here is because we already have an Ord for this part of the type. So if we define rank beats, if we derive Ord, then the rank beats function, we have rank 1 and rank 2. Rank 1 beats rank 2 precisely when rank 1 is bigger than rank 2, strictly bigger, in the ordering that we derived using the deriving clause. Okay, that didn't work. Why didn't that work? Well, the reason is because in order to be in the Ord class, let me go back to the information about Ord. We're almost there. We need to know about one other class. If you want to be in the Ord class, you also have to be in the EQ class. So what is the EQ class? That should be fairly obvious. The EQ class, which also lots of things are in, are the class for the equality and inequality operations. So if I just comment this out for a second, and let's just derive show for now. You notice that I had to put brackets around it when I wanted more than one deriving clause. If I reload the file without any errors in it, is red equal to black? Are those equal? Well, your intuition would tell you that that's not true. But in fact, what Haskell says is we don't have an equality function for these guys. So in order to do that calculation, to ask whether two colours are the same, we need to derive not only show, but EQ. So if we derive both show and EQ, then we can ask whether red is equal to black, and of course that's not true. So we need to do the same here. We need to derive not only show, but also EQ. So they're the three type classes that we are going to mention in this lecture. We will, of course, talk a lot more about type classes later, but for now you just need to know that for certain operations to be automatically introduced, like operations for printing a value on the screen, testing for equality or inequality, then we can do that in a simple and lightweight way by asking Haskell to derive suitable functions automatically from the definition of our data type. And it will derive, as it were, the obvious definitions. Equality will ensure that two numeric cards are equal, providing their ints are equal, two jacks are equal, two queens are equal, and so on, and everything else will not be equal. So if you imagine that you had this big, hairy, complicated looking definition, it would be quite nice to test it. So what might these suitable testing functions be for such a definition? The definition that we've got based on deriving Ord is very simple, so this is really would be rather unnecessary in this case, but it's a useful exercise to think about how you would define a reasonable function for prop rank beats. When you do quick check, for example, quick check can also help you find missing cases, incomplete definitions, inexhaustive patterns as we call them. That's because it will test all sorts of values and indeed throw values at it that will cause exceptions, and quick check will report those. But let's think about what a property of rank beats might be. So what we would like is that rank beats R1, R2, or the other way round, or in fact they're equal. So there are three possible cases: either rank beats R1, R2, rank beats R2, R1, or they're equal. So that means we need to use the Boolean OR function, the logical OR. And you saw earlier that I used this AND function. I just pulled it out of a hat and used it. And you're at the stage where you expect to see every function you'll ever need in a video. So you need to be able to find things. So I'm going to say a few words about how you might go around finding things. And one way to do that is to use a search engine called Hoogle. So Hoogle is a search engine. You can find it under hoogle.haskell.org. And what it allows you to do is to search I'm going to search, let me search using it, search the Haskell platform. And what am I going to search for? Well, I can search for things by name. So if I know the name of things, if I was looking for the abs function, for example, I could find it, or not, for example. A function takes bool to bool. It tells me where it's found. It's in the prelude. And there are lots of other variants in related functions. But I'm not going to search by name. I think one of the cool features of Hoogle is that it allows you to search by type. We're looking for something for combining two Boolean values. We're going to combine rank beats R2, R1 and rank beats R1, R2. And we want whatever the OR function is. I don't know what it is at the moment. Well, I do know what it is, but let's just suppose I don't know what it is. But we do know something about it. We know its type. We know that it takes a Boolean first argument, a Boolean second argument, and returns a Boolean result. So that's the type signature of the function we want. And what Hoogle has done is searched according to functions which match or are similar to this signature. So here is a bunch of operations that we can use at this type, and the ones that we have which are matching exactly this type are the AND function that we saw before. That was this guy here. And here's the one we actually want. In this case, it's the OR function. It's written as 2 vertical bars. So that's the OR function. And then there was one other case we wanted that R1 is equal to R2 when neither of them beat each other. Now we might want to use an exclusive OR function between these three. We only have a binary version of exclusive OR, and that's actually implemented by using the not equals function. But that's not quite what we want. So if you want to actually define this more precisely, it's one of these three possible Boolean expressions that should be true, exactly one of them. You'd have to define a function for that, I think. Or you compute one of them twice, maybe. But anyway, so that's an quick introduction to Hoogle that may help you find functions. And if they are in the prelude, then they're nothing you have to load. But if they're not in the prelude, in some other package, then you will be able to see which package they're in. And you can choose, if you're using Haskell platform, you will need to install it using Cabal. If you're using Stack, then you will install it using Stackage, and it will tell you where to find them in Stackage. And you'll see that there's a lot more functions in via Stackage in this particular case. Okay, so that was the Hoogle stuff. And we've already talked about don't care patterns, so I'm not going to talk about those anymore. Okay, so now we've got a nice property, so we might think about testing that using quick check. Unfortunately, we can't do that just yet, because when we introduced new types, we also need, in order to use quick check, to tell quick check how to generate random values of that type. That's not something that is automatic, and so that will be a topic for another lecture. So we won't actually run quick check just at the moment on these things, and in the lab we'll give you the code you need to be able to run properties on these kind of data types. So you won't need to define those yourself, and we'll come to those in a later lecture.